In this section, we'll talk about the concept of the partial derivative. In Cal 1, you first define a derivative with the following definition. We say something like, let f of x be a function. Back when we only had functions of a single variable. Good times, yeah? Let f of x be a function then the derivative of f of x is, first of all, denoted by, you can either use the Leibniz notation, d dx of f of x, or well, more often we use the Newtonian notation, f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x over h. And although there are a few variations on this definition, they are ultimately all the same thing. Note the language used here, the derivative. There's only one. If I give you a graph and I ask you find the derivative of the function at a particular point, you're going to get a unique answer. Now, of course, it's possible the derivative doesn't exist. All right, so it's possible you get no answer. But if you do have an answer, then there's one and only one. The derivative is unique and is often associated with the slope of the line tangent to our curve. Now remember, the derivative is not the tangent line. However, the derivative gives us the slope of a line tangent at a point. But now we're looking at functions of multiple variables. So here I should say recall. Which means we're dealing with surfaces. So let's consider a surface. In full disclosure, I actually walked around my house for about 15 minutes looking for an object that was adequate. And what I found was this. It's a hex wrench used for putting together furniture and, well, anything with that kind of a fitting there, right? So consider the following surface. Okay, I was going to actually try to draw this, and I realized, no, it would be far simpler if I just go ahead and grab something of an appropriate shape. All right, now, let's say I asked you to find the derivative at this point, right here. You say, well, what do you mean by derivative? Well, okay, you're going to get a number, but think of it as the slope of the tangent line. Granted, those are not the same, but they, granted that the derivative is not exactly the tangent line. However, one of its uses is giving us the slope of the line tangent. Okay, that's fine. So if I'm standing at this point right here, imagine I'm very, very tiny. I'm a little ant or a little bug sitting right here. Okay, well, on the plane, it's pretty simple. If I'm standing right here, I can start walking. A little tiny bug walking this way. And which way am I walking? Well, there's the direction I'm walking. Or if I started walking this way, again, there's the direction I'm walking. And although that will change over time, at this exact moment, that's the direction in which I'm walking. But if I do that on this surface, that's not really well defined, is it? Because if I'm sitting at this point, well, which way, what's the derivative? Okay, so start walking and tell me what the slope is. Well, which way am I walking? Notice if I start walking this way, I'm walking uphill. It's getting thicker up here, right? So if this is laying flat and my little bug is right here and they start walking, they're walking uphill. They have a positive slope. But if they start walking this way, well, that's a negative slope. They're walking downhill. And if they kind of walk diagonally, well, this part's uphill and this part's downhill, but here in between, it's kind of flat. So if I ask you for, okay, if you're standing right here, start walking in some direction. Give me the slope of that line. Give me the slope of the tangent line. That's not a well-defined question. I don't even know what you mean. If I walk this way, it's a positive slope. This way, it's a negative slope. And this way, it's, well, it seems like it's perfectly flat. It seems like I'm not getting any higher or lower. Okay, so then this concept of the derivative, it doesn't quite apply to a surface, something in 3 dimensions. Okay, so does that mean we just don't have a derivative? Well, not quite. It just means that it's not unique. We no longer have the derivative. Rather, we're going to have a particular derivative. At a particular point, I can still find a direction in which my little bug is walking. However, it depends on which way they go. So this brings us to our updated definition, where we define the partial derivative. Here, one thing you'll note is it looks very similar to this, which of course it should. We're defining a derivative. Let f of x comma y, so we have a function of two variables now, be a function. Okay, so it's no longer a function of one variable, now we have a function of two variables. Then we define the following derivatives, two of them. First, a little bit of notation. That's a subscript. That's not f of x, it's f with a little subscript of x, of xy. This is equal to the limit. Okay, so they're still defined as limits. As, we could use the letter h here, but since I'm going to have more than one derivative defined, if I use h for one and then h for the other one, they're going to mean different things. So that could be confusing. So instead of saying h, we're going to say delta x. We want the limit as delta x approaches 0. This delta x is playing the same role as this h. It's going to be a little something that's going to go to 0. Okay, we're going to take the limit as delta x approaches 0 of f of x plus delta x. You say, well, that's the same thing, right? F of x plus delta x. It's just, instead of an h, you're writing delta x. Oh, but wait a minute. That can't be right. Because notice, my function's supposed to have two arguments. It's supposed to have an ordered pair as an input. Oh, okay. So then here, that shouldn't be the end of my parentheses. That should be a comma. So there should be f of x plus delta x comma y minus f of x comma y over delta x. This is called the partial derivative with respect to x, sometimes also called the partial derivative in the direction of x. However, I believe this textbook uses the language of with respect to x, so I'll continue that. This defines the partial derivative with respect to x. F sub y of x comma y, you have a subscript of y instead of an x. This should take no imagination to realize what we're about to do here. Notice here, we left y the same. If you ignore those two y's that were left the same, that definition is exactly the definition that we had from Cal 1. The limit as something approaches 0 of f of x plus that something minus f of x over that something. That's a derivative with respect to x. The derivative with respect to y takes zero imagination to realize we're about to do the exact same thing, but to y instead of x. Let's take the limit as delta y approaches 0 of f of x comma y plus delta y minus f of xy over delta y. And this defines our, and it should take no imagination to realize what we're going to call it. It's called the partial derivative with respect to y. Provided that these limits exist. Okay. From a practical standpoint, yes, the definition is stated as a limit. But if you think back to Cal 1, we didn't often, no, we did sometimes, but we didn't often actually use the definition of the derivative. Instead, we often had some nice algebraic shortcuts. There's some nice results that we got from theorems, like the use of the sum rule, the difference rule, the product rule, the quotient rule, the chain rule. We're going to have, from a practical standpoint, we're going to have some nice results for the partial derivative. Before we even get to those, note, what you can think of partial derivatives as is, okay, here's your surface. Okay, now here's your z-axis coming up toward the camera. Okay, forget about the z-axis. Here we only want x and y. Okay, well, the z-axis is coming straight up toward the camera. The x-axis is going left to right, and the y-axis is going this way. Z is coming up toward where right now where you're watching. Okay, what the partial derivative with respect to the x-axis is, okay, where's your little bug? Oh, they're sitting right here. Okay, what's the slope of the line that they're traveling along? Well, what line? Oh, the line that's parallel to the x-axis. Oh, okay, then the slope is positive 1/8, or whatever it might be. Oh, I'm sorry, I didn't mean parallel to the x-axis, I meant parallel to the y-axis. Oh, then that's what the partial derivative with respect to the y-axis is. The little bug is standing somewhere. What's the slope of the line along which they're traveling? Which line? Oh, the one parallel to the x-axis. Oh, that's the partial derivative with respect to x. The partial derivative with respect to the y-axis would give you the slope of the line as they travel parallel to the y-axis. Now notice that's only those two directions, along the x-axis, along the y-axis. What about in between? What about this way? What about this way, diagonally? Can we define those? Yes, we'll talk about those in the next section. We'll talk about directional derivatives. But for now, we're looking at specifically the two partial derivatives. So here, note, from a practical standpoint, a practical method for evaluating a partial derivative is to consider all variables except the one you differentiate with respect to, as a constant. As constants. So for example, consider the function f of x comma y is equal to 2y squared root x. Let's go and compute our partial derivatives. What is f sub x at x comma y? You're differentiating with respect to the x-axis. So back to our visual. That means that your little bug is going to walk parallel to the x-axis. Well, whenever you have a line that's parallel to the x-axis, the y variable is constant. For example, if this is the point 3 comma 5, and I walk parallel to the x-axis, I'll hit 4 comma 5, 5 comma 5, 6 comma 5, 7 comma 5, 8 comma 5. Oh, that y value is always constant. So since I'm differentiating with respect to the x-axis, that means I'm walking along a path parallel to the x-axis, and so that means that my y variable is being my y variable has a value that's being held constant. So here, to take the partial derivative, consider this a constant. Okay, so whenever I take the derivative of a constant times the square root of x, I get that constant times 1 over 2 root x. If I was taking the derivative of 3 square root of x, what would I do? I would say, okay, well, when I take the derivative of a constant times a variable expression, I can pull the constant out. Okay, so the 3 just stays a 3. The square root of x has a derivative that's 1 over 2 root x. So it's that constant times that derivative, 1 over 2 root x. But here, this is being treated as a constant. Is it a constant? Of course not. It's a variable. But for the purposes of taking this derivative, it is constant. So here, this was considered constant. While computing the derivative. I'll say while computing f sub x. And now you can simplify. The 2's divide out, and you're left with y squared over root x. And that makes us happy. We can do the same thing with the partial with respect to y. We can simply say, okay, if the partial is with respect to y, that means y is the variable. Everything else is a constant. So here, I might even want to rewrite this as 2 root x y squared, just because I want my constant all to be together. Remember, when you take the derivative of constant times y squared, you just take that 2, bring it down, multiply it with this constant, subtract 1 from the power. So here that would be, leave your constant the way it was. Now take this 2, bring it to the front, and then subtract 1 from the power. So that's just power 1. And then multiply this out, and that'll give us 4 root x y. And there we go. Those are our partial derivatives. From a practical standpoint, you can consider partial derivative as I'm taking the derivative while holding everything else constant except for that one variable. Go ahead and give this a try. All right, so let's have f of x comma y equal to the natural log of the square root of x squared plus y squared. Okay, go ahead and find the 2 partial derivatives. First one is find f sub x of x comma y, and then the second question will be find f sub y of x comma y. Okay. Go ahead and pause the video, give that a try. Once you're done, go ahead and unpause and we'll go through it together. All right. When I'm going to take the derivative of the natural log of something, that's going to be 1 over that something. Okay. So it's going to be 1 over that something. And it doesn't matter if that something is a variable or a constant or a... Well, actually, I guess it does matter if it's a constant, right? The natural log of a constant would be constant and the derivative would be 0. But here, if you're taking the natural log of a variable expression that has variables and constants, it doesn't matter what they all are. You're just going to take 1 over that whole thing. But now, you have to take the derivative of this part, because of the chain rule. Take the derivative of the natural log of something, it's 1 over that something times the derivative of that something. Okay, so now we have to take the derivative of this thing. Okay, well, if I take the derivative of the square root of something, that's going to be 1 over 2 root of that something. Oh, but now I have to use the chain rule again. Take the derivative of the inside. Okay, so times the derivative, and now here's where this comes in. I have to worry about which one of these is a variable and which one's constant. Here, x must be my variable. So when I take the derivative of x squared, that'll give me 2x. Plus, when I take the derivative of y squared, that's going to be 0, because now y is a constant, at least for the purposes of this partial derivative. So the derivative of a constant must be 0. And there we go. We can now simplify this. Notice these 2's divide away. Your square root of something times itself is, well, the square root goes away, right? So that's going to give us x in our numerator over x squared plus y squared. Just like that. This one will be very, very similar. You take the derivative of the natural log of something. That's going to be 1 over that something. But now chain rule, derivative of this part, the argument of the logarithm. Okay, well, the square root of something, okay, the derivative will be 1 over 2 root of that something. Oh, but now I have to use the chain rule again. I take the derivative of this innermost part, x squared plus y squared. What's the derivative of x squared? It's 0. If you're taking a partial with respect to y, x is a constant, which means x squared is a constant. And the derivative of a constant would be 0. Plus, here, I want to take the derivative of y squared. Okay, y is a variable, so here I can use the power rule. Take my 2, bring it down, subtract 1 from the power. And now I can simplify. Here the 2's divide out, and if I have the square root of something times itself, that's the square root squared. Okay, the square root goes away, the square goes away, and we're just left with the argument. So here this gives us a y in our numerator over x squared plus y squared as our result. And that makes us happy. All right. Before we continue, a little word on notation. A little word on how we write things. Okay. When we have a function of one variable, it's very common to write y equals f of x. Y equals f of x. So when we take the derivative, and here there's only one, we can write it as y prime is equal to f prime of x. Newtonian notation works wonderfully with a single variable because there's only one derivative. If I say prime, I know which derivative I'm talking about. Now, of course, that was not the only notation. Newtonian notation was not the only one available in Cal 1. We also had Leibniz notation, which is d dx of y, or dy dx. And that would be d dx of f of x. So you can either say dy dx or df dx. And if this is our function, then these are our derivatives. Well, now we have functions of two variables, x and y. Okay, so here we need a third variable. So here, that's x and that's y. Here, that's x and y, so we can call this z. Z is equal to f of xy. We've seen that before. You would not be able to say z prime because it doesn't make any sense. Which one? Which variable, which partial derivative are we taking? There's more than one derivative. So in this case, instead of saying prime, you see we've been using the subscript notation. So instead of having a prime up here, we have a subscript. Note there are two different derivatives. We can say f sub x. I guess I should write it the way I did over here. So here we can write this as z sub x is equal to f sub x of x comma y. So you can either write z sub x or you can write f sub x. And likewise, you can write z sub y, which as you see here, we've been writing as f sub y of x comma y. So we don't use prime notation at all because it's not specific enough. Instead, we use the subscript notation. Leibniz notation has not been affected because, of course, here we were specific about which variable we were differentiating with respect to. We're differentiating with respect to x. Okay, so that's exactly what we need here. So we will continue to use a similar notation. Similar, not exactly the same? No, not exactly the same. Here, whenever we have Leibniz notation, we use the letter d, like this, d dx. Here, we want to make explicit the fact that we're talking about a partial derivative. We don't want anyone to say, oh, I'm sorry, I thought you meant the regular derivative with respect to x. I didn't know you meant the partial derivative with respect to x. I thought we were talking about regular differentiation. I thought we were talking about maybe implicit differentiation. I didn't know we were talking about partial differentiation. So in order to distinguish the two, we're going to use a very similar notation, but instead of d dx, we use the Greek letter del. Del x, which might sound a little funny, might feel a little strange coming off the tongue, but del x is a commonly accepted notation. So here we can say del x of y, or of z, sorry. Or you can say del z del x, either one's fine. And that's going to be del x of f of x. I do apologize here. A lot of people have told me my del's look like the number 2. They might look like other people's number 2, but they don't look like my number 2. Notice my number 2 looks like this. So just as a quick heads up, I do apologize. I know it does look a lot like the number 2. Here, this is del. This is the number 2. And this is the letter Z. Z. For those across the pond. That might look like your number 2, but it definitely does not look like my number 2. And that might look like your letter Z, it definitely does not look like my letter Z. All right, so just a quick note. If you got a little loop-de-loop here, that's del. I do not write my 2's that way, as you can see above. And also take a moment to appreciate the fact that at least we do try with our notation. Many years ago, I was an undergraduate student, and I had a professor who liked to use some unorthodox notation sometimes. There is a Greek letter whose capital version, not the lowercase, but the capital looks like this. It's pronounced C. Okay. Now, in complex calculus, complex analysis, calculus that uses complex numbers, if you have a variable and you want to take its complex conjugate, you put a bar over it. So this would often be just called x bar. Okay. Now, imagine taking this and taking its conjugate. Okay, well then it would have a fourth little bar up here. Our professor one day came in, our beloved professor came in and said, he started talking, and he said, okay, consider the function xc. Now consider the quotient of xc with its conjugate. So the man then proceeded to write this. And then talked at length about it. And yes, I suppose it is an acceptable notation. That's xc divided by its own conjugate. However, here I've taken a bit more care to write it in a clear way. I believe what he wrote was this, which to this day we don't really know if he was messing with us or not. But in any event, at least we do try to keep things clear. Here, del x has a counterpart, del y. And that would, of course, be the partial with respect to y. So del y of z, or del z del y if you prefer, is del x of f of x comma y. Oop, I forgot one of my arguments here. There we go, x comma y. So here we have either the subscript notation, or we continue with Leibniz notation. We just kind of take our d's and curl them a little. Note that to evaluate a derivative at a point, we are going to continue to use the notation that we had in Cal 1. Namely, we're either going to just write the numbers in here or with a vertical bar. So here, to evaluate at the point, let's say a comma b, you would write del z del x at a comma b. So you put the vertical bar with that right there, what you're trying to evaluate. You would write del z del y at a comma b, like that. Or if you're using this notation, you might write something like f sub x at a comma b. Or you might write something like f sub y at A comma B. That would be the same as that. This would be the same as that. Assuming you had something like z equals f of x comma y to begin with. So for example, again, let's have a function, f of x comma y equals to e to the minus x times the cosine of y. Something like that. Okay. Let's say we want to find del f del x at 0 comma 0. All that means is take the derivative of the function with respect to x and then plug in 0, 0. All right, so let's give this a try. First of all, we're going to take the partial derivative. Here, x is your variable, y is a constant. Okay, well, let's see here. If you have y is a constant, that means cosine of y is a constant. But its derivative is not 0, because here these are not being added. They're being multiplied. So it's like saying this is a coefficient. If you have e to the minus x times a number, take the derivative, you still have e to the minus x times the number, but then you got to multiply by the derivative of the negative x, which is a negative 1. All right, so here, it's like saying I had 2e to the minus x and I took the derivative. Again, nothing would happen with the 2, it would just stay at 2. We would just take the derivative of this part. Like that. Same idea here. This would be e to the minus x times cosine of y. Oh, but now because of the chain rule, we'd have to take the derivative of this argument, which is just a negative 1. Okay, so there's my derivative. And I'm evaluating at 0 comma 0. Okay, so now plug in a 0 for my x. And plug in a 0 for my y. Which is what? E to the 0 is 1. Oh, but we have a negative, so that's going to be negative 1 times cosine of 0 is 1. So here our partial with respect to x of f at 0, 0 is negative 1. So you graph this as a surface. Okay, now sit at the point 0, 0. All right, now start walking along the x-axis. You're going to have a slope of negative 1. Okay. We could do that same thing for the other direction. We could say del f del y, and again we could do it at the same point. Note that walking in different directions may give you a different slope. Here we're taking the derivative with respect to y, which makes this a constant. X is a constant, which means e to the minus x is just a constant. So if I take a constant times the cosine of y, the derivative would be negative the constant times the sine of y. The negative because the derivative of the cosine is negative sine. So here we get negative e to the negative x times the sine of y, evaluated at 0, 0. And now go ahead and plug in 0 for x and y. So this would give us negative e to the 0 times sine of 0, which is negative 1 times sine of 0 is 0. Oh, the whole thing is 0. And there we go. I suggest you give this a try here. Given how much we used derivatives in Cal 1, you should rightfully suspect that we're going to be using partial derivatives a lot for the remainder of this course. So a good amount of practice is probably a good idea right here. Go ahead and give this a try. Take the function h of x comma y is equal to x squared minus y squared. Find the slope in the direction find the slope in the direction of find the slope in each direction, meaning along the x-axis or along the y-axis, at the point negative 2, comma 1, comma 3. A little bit more should be said here. Here, what we're imagining is we're imagining a surface. So here, if you had z equals x squared minus y squared, if you took the moment to graph it, you would end up with a hyperbolic paraboloid. Notice level surfaces here, those are hyperbolas. X squared minus y squared equals constants. Those are hyperbolas. But if you take traces like this, x squared is a constant. Y squared is a constant. Then you'd have z equals x squared. Okay, well then that's a parabola. And same thing over here, that's a parabola. Z equals negative y squared. So here we have a parabola. Here we have a parabola. But then if we make this a constant to get some level surfaces, we'll end up with hyperbolas. So this graphs out as a hyperbolic paraboloid. So here's a rough sketch of our object. Here, the part that I'm drawing in blue, you can kind of imagine this as being like the outside of a tunnel, and the part in gray is like the inside. You're kind of going through in there, and that's what your object would look like. So here what this is saying is, okay, here's your surface. Now you happen to be sitting at a particular point. That point, let's go ahead and do that in red. That would be negative 2, 1, 3. So there's your point. You're right up there on that part of the surface, and that's negative 2, 1, 3. And now the question is, okay, now start walking in each direction. What do you mean each direction? I mean along the x-axis, and then separately along the y-axis. If you go along the x-axis, what's your slope? You go along the y-axis, what's your slope? Right? It's a slightly bit. This is a slight bit more visual example than what we just had, but it does still work out the same way. So go ahead and give this a try. Pause the video and find the slope in each direction, along the x-axis and along the y-axis. Once you are done, go ahead and unpause and we'll go through it together. All right, so to account for the two different directions, what we can do is we can take the partials with respect to both axes. Let's begin with del f del x. Now we're going to evaluate this at, notice we don't have anywhere to plug in z, so you're just plugging in x and y. So if you want to write the point negative 2, comma 1, comma 3, you can, but since we don't need the z anyway, it's sufficient to just write negative 2, comma 1. If you wrote all three, that is still correct. So we want the partial with respect to x at that point. All right, well, the partial with respect to x. Okay, the derivative of x squared is 2x. The derivative of minus y squared is 0. This is a constant with respect to x. And if you have x squared plus a constant, taking the derivative of that constant gives you 0. So here you can write plus 0, or probably better off just not writing anything there. And now we can evaluate this at negative 2, comma 1, which will give us negative 2 times 2. Right, there's nowhere to plug in that y, so don't worry about it. Just plug in your negative 2 times 2, which is negative 4. So if you're at that point right there, and you're walking along the x-axis, your slope is negative 4. You're going downhill. On the other hand, if we take the partial of f with respect to y at that exact same point, that's going to give us, okay, well now the derivative of x squared is 0 because x is a constant, y is your only variable, and the derivative of minus y squared is minus 2y. and that's going to be evaluated at negative 2 comma 1. There's no way to plug in that negative 2, so don't worry about that. Go ahead and plug in your 1. Negative 2 times 1, that's negative 2. So if you're standing at that point, you want to go down to the ground. Notice you're up here 3 steps above the XY plane. If you want to get down to the XY plane, if you traveled along the x-axis, it would be very steep. If you traveled along the y-axis, it would still get you down. Still got a negative slope, but it's a lot less steep. And we want to go rock climbing. One thing you should note is, of course, this can be extended to any number of dimensions that we like. Although we may not be able to draw it. This can extend to any number of variables. So, for example, I could say something like, let's take a function w equals f of x comma y comma z, and that's going to equal to, let's just keep this simple for right now. Let's say sine of x minus y to the 5th plus e to the power z. Okay. Then if I wanted to take the partial with respect to x of my function, well, then that would simply be same as before. I can consider y and z to be constant. So here that would be a constant to the 5th power, which is a constant, and that would be e to a constant, which is also a constant. So here the derivative would simply be the derivative of the sine of x, which is the cosine of x, and then these derivatives would be 0. So I could write plus 0, or probably just better off leaving it like that. I could take the partial of f with respect to y, and of course, that would make both of these constant, and so their derivatives are 0. The only derivative that I would be left with is the derivative of minus y to the 5th is minus 5y to the 4th. And I could also take the partial of f with respect to z. And here, these would be constant, therefore the derivative would be 0, and so e to the z has a derivative that is, well, itself. Just like that. Okay. Now, in Cal 1, you first find the derivative and start using it to talk about the slope of a line tangent to a curve at a particular point. But then you quickly find uses for higher order derivatives. You take the second derivative and use it to talk about concavity, for example. Here, we can also talk about higher order derivatives for partial derivatives. However, because there is more than one first partial derivative, then there's going to be several second partial derivatives. So, higher order partial derivatives. All right. Let's say I take a function and take its derivative with respect to x. Well, okay, that's not the only one that I could do, right? I could also take a function and take its derivative with respect to y. You say, why are you putting so much space in there? We don't want so much space in there. That means you're going to write a lot more. Yeah, well, it is what it is. Here, I take a function. So first of all, let's go ahead and let f of x comma y be a function. So here we're dealing with functions of two variables. Okay. This is the first partial derivative with respect to x. This is the first partial derivative with respect to y. Okay, so now it stands to reason that I could just take a derivative again. Okay, so take the derivative of this. Which one? You want me to take the derivative with respect to x or y? Well, you already took the derivative with respect to x. Yeah, so what? this is going to give me some new function. So I could take its derivative with respect to x or y. So that is going to give us, so these are the first partial derivatives. First order partial derivatives. But if I take the derivative of this one, well, there's two derivatives I could do. The way it's denoted is like this. Here, you say, okay, you take the first derivative with respect to x and the second derivative also with respect to x. Or you could take the first partial derivative with respect to x, and then the second one you can do it with respect to y. Likewise, if you took the first partial with respect to y, you could say that's going to be f sub y, and then take the second partial with respect to x. Or you take the first partial with respect to y and the second one also with respect to y. So notice there are two first order partial derivatives. There are four second order partial derivatives. You'll keep doubling. If you need a third order partial derivative, well, there's going to be 8 of those. Because you could say xxx, xxy, xyx, xyy, yxx, yxy. You could say yyx or yyyy. So that would be 8. So 2, 4, 8. You wanted a fourth order partial derivative? Well, there'd be 16 of those. Thankfully, we have no use for those in this course, but hypothetically you could. Okay. So these are our second order partial derivatives. Since we're talking about vocabulary, these two right here, these are called the mixed partial derivatives. When you could take both derivatives with respect to x or with respect to y, but here, if you take one with respect to x and the other with respect to y, these are called the mixed partial derivatives. In terms of notation, we saw how f sub x can also be written as del f del x, and f sub y can also be written as del f del y. Your second order partials can also be rewritten as follows. F sub x x can be written as, it's going to look like Leibniz notation for the second order partial in Cal 1, except you're going to have del instead of d. So here we can write this as del squared x over, del squared f over del x squared. If you want to write f sub y, that would be del squared f over del y squared. It's the mixed partials that are sometimes a little unpleasant to write. If you write fxy, that's del squared f over del y del x, which is slightly confusing because xy and here it's written as yx. And if you want to write f sub yx, that would be del squared f del x del y. Like that. So here is the Newtonian notation. Well, actually, it's not really the Newtonian notation. It's the subscript notation. Subscript notation, and then here you have the Leibniz notation, the del notation. These are equivalent. but, well, I think people tend to prefer these for obvious reasons, but this is equivalent. So as an example, regardless of which notation you want to use, let's let z, sorry, if you prefer f of x comma y, z is equal to x to the fourth minus 3x squared y squared plus y to the fourth. Find all second order partial derivatives. Find all four of these. First, you're going to have to find the first partials, and then from there you can find the second partials. So go ahead and give this a try. Pause the video, and once you're done, go ahead and unpause, and we'll confirm these together. All right, so let's go ahead and take a look. First, we're going to find the first partial with respect to x, and then we'll be able to find these two. All right, the first partial with respect to x. Okay, well, that's x to the fourth power, so just use the power rule. Break your 4 down, subtract 1 from the power. Here, notice that y squared is a constant, along with the 3. So if you had a constant times x squared, and you're going to take the derivative, you would simply take your 2, bring it down to join this constant times your x, which is exactly what will happen here. This constant will stay exactly as it is, negative 3y squared. That is constant. But now the 2 will come down and join it, so that'll be negative 6y squared times your x. Or negative 6xy squared. Either order is fine. And then, of course, here the derivative of this is 0, because with respect to x, it's a constant. So now from here, I can go ahead and find the partial, the second partial with respect to x. So this is the first partial with respect to x, and now I apply the partial with respect to x again to this result. Okay, well, that's going to be just the power rule. Take your 3, bring it down, subtract 1 from the power. So that'll give us 12x squared. And then here, again, this is a constant times x. The derivative of a constant times x is just the constant. So minus 6y squared. And there we have it. There's our first partial. There's our first of 4 second-order partial derivatives. Let's go and take a look at z sub xy. So we start with a partial with respect to x, and then apply a partial with respect to y. Okay, well, here's our partial with respect to x. If I take the partial of this with respect to y, I get 0, because here this is a constant with respect to y. Okay, so I don't worry about that one. If I take the partial with respect to y of this one, okay, my minus 6x is a constant. So constant times y squared. Okay, I'm going to take my 2, bring it down to join the constant, giving me minus 12x. And then since that has lost the power, it's now down to power 1. So we can say that's minus 12xy. And these are the first 2 second-order partial derivatives, xx and xy. So now let's go and take z sub y. And that's going to be, well, let's see, starting back from the original. With respect to y, this whole thing is a constant, so its derivative is just 0. We don't worry about that one. Okay, with respect to y, this negative 3x squared, that's just a constant. So constant times y squared, take your 2, bring it down. It gives us a minus 6x squared, and then you brought your 2 down, so now that's just power 1. Plus, and then the derivative with respect to y of y to the fourth, that's just the power rule. Take your 4, bring it down, subtract 1 from the power. Looks very similar to this one. Now, let's take a look at the second order partials that start with a y here. Let's start with z sub yx and then z sub yy. Z sub yx, okay, we start with z sub y, and I'll take its partial with respect to x. Notice the partial with respect to x here would be negative 6y would be a constant now. So now I will take that 2, bring it down to join the constant, giving me minus 12y. And then since the 2 has lost the power, since the x has lost the power of 2, it's down to a power of 1. So that'll be negative 12xy. One thing to note, these are the same. That is not a coincidence. There's a theorem coming up here in just a moment which will confirm for us that these should be the same under appropriate conditions. Finally, z sub y, that's, well, we're going to take the derivative of this with respect to y. Okay, well, with respect to y, this is basically just a constant times y, and the derivative is just that constant. So minus 6x squared. And then here, the derivative with respect to y, okay, take your 3, bring it down, subtract 1 from the power. These are not the same. They're not terribly different, but these two are exactly the same. Finally, we close our section with that theorem. And this is the theorem that talks about the equality of mixed partials. So in fact, let's even title it. This is about the equality of mixed I was contemplating whether I should write mixed second order partial derivatives, but well, when we say mixed, we mean second order anyway. Mixed partial derivatives. Let f of x and y, you have a function of two variables, let f of x comma y be a function that has, I guess I should say such that, let's say it that way, such that f sub xy and f sub yx, the mixed partial derivatives, are continuous. On an open disk R. Then, for all points in R, we have that f sub x y at x comma y is equal to f sub y x at x comma y. So here, as long as your mixed partial derivatives exist and are continuous on an open disk, then they must be equal to each other. Going back to the problem we just saw, here we did find the mixed partials. These are both continuous. In fact, they're not just continuous on some open disk, they're continuous on the entire plane. So I guess you could say it's a disk of infinite radius. Either way, this is continuous for all real numbers. After all, it's polynomial, and so is that. So here, because both partials exist and are continuous, they're polynomials, of course they're continuous, then obviously they must be the same. Right? The only time where you would have these not be the same is if one or both either did not exist or were discontinuous at the place we were observing. Here, the proof of this one requires the use of iterated integration, which is something we haven't seen yet. So here, the proof of this is omitted. Since it requires what are called iterated integrals. And since we haven't talked about those at all, and we haven't gotten to anything that involves iterated integration, then, well, the proof is not exactly accessible right now. I could write it, and it doesn't really mean anything just yet. So we'll say, okay, this is true, and it can be proven. And here we see an example, but unfortunately, we're not going to prove it rigorously because at the moment, it's not really accessible. So that does bring us to the end of our section. If anybody has any questions, comments, or problems, please make a note of those and reach out. And I hope everyone has a nice day.